So, welcome back. Um, Here's just a cool little thing to show you. So, today we're looking at nth terms of interesting sequences. You'll see what this means a bit later on. But let's start with quite a famous problem. It's known as the Tower of Hanoi. Essentially, you have three sort of poles, and you have a couple of disks on the first pole. Let's say you have n disks in total, and you want to move all of these disks over to another pole with the one rule that you can't put a disk that's wider than a disk below it onto the pole. So, for example, for 2 disks, um, you move the first disk to one of the poles, then you move the second disk to the other pole, then you move the first disk on top of the second disk. Similarly for 3 and so on. However, there's actually quite a cool thing with this, and that's, so let's say you have n plus 1 disks. Now, you know how many times it takes you to move n disks, so you do that. Then you move this disk once. Then you move all the n disks there again. And that means that so let's call the amount of time we're trying to find out the nth term of so we're trying to find out, given you have n disks, how many moves do you need to make. So let's call this hn. We know that hn, we know that h1 is equal to 1. That's kind of obvious. And we know that h2 is equal to 3. Demonstrated that. And now what we've worked out is that hn is equal to hn minus 1 plus 1 plus hn minus 1, which is, of course, 2hn minus 1 plus 1. Now from here, if you think about this, like sort of putting this equation back into itself over and over and over again, you get this type of thing. I'm going to be slightly lazy here. And so on and so forth. Now, what this actually ends up looking like. And I mean, you can see a pattern emerging. So let's do this like to the absolute extreme. You can see there's both a 3 there and a 3 there. To the 0 is equal to 1. And since h1 is equal to 1, you can basically just remove that. And this is actually quite easy to find out what you can simplify this quite easily, because this is just, if you add 1 to this, those two become a 2 to the 1, the next two become a 2 to the 2, and so on, until you get all the way back up to hn. However, you don't have an extra 1 there, so it's just hn minus 1. Now, this is quite a cool trick. However, you can take this slightly further. Using a different famous sequence. Fibonacci numbers. Let's call so a few things we know about the Fibonacci numbers. We know that the f of n, this is like the nth Fibonacci number, is equal to the sum of the last two Fibonacci numbers. And we also know that the first two Fibonacci numbers are both 1. Now, what we're basically trying to express the Fibonacci numbers as is a power. So instead of calling it sort of fn, let's set this equal to a to the n. Now, through this, we know that a to the n is equal to a to the n minus 1 plus a to the n minus 2. However, this form is really awkward for us, because you have not only one, but two different sort of previous terms. Now, we've already seen you can do certain things to get rid of one previous term, but getting rid of two is a lot more difficult. However, through this equation, we can actually get a few different solutions. So first of all, let's just take a look at the second Fibonacci number, which we know from here is 1. So this gives us that a squared is equal to a plus 1, because a to the 0 is always 1. And this is essentially just a quadratic equation, which, thankfully, we can solve. And using the quadratic formula, this isn't very difficult. Let's call the roots of this equation x, 1, and 2, because I can't be bothered to write the actual roots in the following stuff, because we're going to be using these numbers a lot. And because of the quadratic formula, these are equal to that. 1 plus or minus root 5 over 2. Now, this is where we finally get to eliminate the one of the two sort of previous terms. Let's set an to be equal to capital A x1 n to the minus 1 plus capital B x2 to the n minus 1. And we can do this because we can quite literally set A and B to be absolute, capital A and B to be absolutely anything. And now let's take a look at a different case. When n equals 1, we get that a to the 1, which we already know because a is the first Fibonacci number, which is 1, is equal to a to the capital A to the x1, 1 minus 1, which is 0, b to the x2, 1 minus 1, which is 0. So this is just a plus b. And now we can take a look again at the second Fibonacci number, which is 1, again. And we get a squared is equal to 1, because, we already know that from all the way up here. And this is equal to something not quite so nice. Obviously it doesn't matter which one of these x1 or x2 is, so let's just say x1 is equal to the plus root 5, x2 is equal to the minus root 5. This is, if we look at these two, I mean, this is just a simultaneous equation. And therefore, we're able to solve for a and b. And this actually gives us that a is equal to, so if you times this entire equation by 1 minus root 5 over 2, then you're able to cancel out the b's, and you get 1 minus root 5 over 2 is equal to a 1 plus root 5 over 2 minus a 1 minus root 5 over 2. And here we can put some stuff in brackets. We can take the a out of these two and just get 1 plus root 5 over 2 minus 1 minus root 5 over 2, which is equal to 1 minus 1 plus 2 root 5, which is obviously just root 5. And so there, now we just divide that entire thing by root 5, and we get a is equal to 1 plus root 5, no, root 5, not root 2, over 2 root 5. And similarly, you can do exactly the same thing almost for b, getting it to be 1 minus root 5 over 2 root 5. Now the really cool thing about the Fibonacci numbers is that this is actually equal to just x1 times by 1 over root 5, and this is equal to 1 over root 5 times by x2. So now, finally, we're able to, using all of the stuff we've done, get that an is equal to 1 over root 5 x1. Well, it's equal to a x to the 1 n to the minus. Basically, we're just taking this and substituting in all the values that we've gotten. And what in the end this becomes is 1 over root 5 times by 1 plus root 5 over 2 times by 1 plus root 5 over 2 to the n. And then, of course, we do exactly the same thing for the other bit, and we get the entire thing, essentially, to equal 1 over root 5, because we can factor this out of a and b. So we get, in overall, 1 over root 5, brackets, 1 plus root 5 over 2 to the n, plus 1 minus root 5 over 2 to the n, close brackets. And this, of course, is equal to f of n. And so, yeah, that's the nth term of the Fibonacci sequence using this method.